physically sound hypothesis. And then we evaluate photometric redshift for each one of these objects using any of these perturbed data distribution. And at the end, we produce a probability distribution function. My colleague statisticians will be horrified because astronomical PDFs are not probability distribution function by any rigorous statistical sense, but this is what they want from us. See, this is what we do. Metaphor has been tested recently on the kilodegree survey, producing excellent results. There you see the average PDF, which turns out to be quite symmetric and quite regular. And right now, basically 2 days ago, Metaphor has also been deployed for test inside the Phosphorus platform, which basically is where the Euclid data center in Geneva is testing the procedure for Euclid. So, I have 2 slides for my conclusion. Machine learning is here to stay. It is a must just because we deal with larger and larger data set, and 99% of this data will never be seen by humans. We have a big problem. We need to move we cannot transfer the data with this large data set. We need to find a smart way to move the programs where the data are. And this has been discussed many times, but has never been truly implemented. I hope it will be discussed in the next status. The use of machine learning method is quite non-trivial. The process needs to be carefully monitored at each step. And there is still a problem with algorithms. Most machine learning algorithms are not fast enough to deal with very large data sets. So there is a lot of work to do in the parallelization of algorithm. And what is more important, they impose a completely new methodological aspect. So my last slide will be about speculations. Since I started with slides from 10 years ago, I hope that in 10 years from now, after my retirement, someone will show this slide. We are in infancy of machine learning. We are still trying to oblige the machines to extract from the data what we want, what we expect is in the data. This is the wrong approach. In the future, data will speak for themselves. Basically, humans will pose questions, then everything from the detector to the final data product will be the results of an automated pipeline, data acquisition, an automated chain of processes which will be largely based on artificial intelligence or machine learning. So astronomers finally will do what they like the best, which is ask the right question and to check, to give the interpretation. But also, and this is why one of the reasons why we are spending so much time in this task, and this is what is written here. Please, I'll ask you 5 seconds to think about this. Physical laws, like most empirical laws, I bet no one in the audience can provide me with an example of violating this law, are based on 3 parameters, independent parameters. Did you ever ask yourself why? Because we live in a 3-dimensional universe, and we have been, by evolution, programmed to recognize patterns only in 3-dimensional spaces. Therefore, all our physics is just a 3-dimensional projection of an higher order physics, much more complex. And I think that machine learning will be crucial in letting us identify this higher order correlation between 5, 6, 7 parameters. So I think that the real treasure behind what's happening now is that we will have a much more complex, much more effective description of the universe, just because we'll be able to discover something which at the moment is not known. Difficult, yes, but you can read it. I think it is feasible after this meeting, because if they could provide us with good internet, and we are a very terrible crowd, I mean, everything will be possible. Thank you very much. Oh, by the way, I think it was Gutzman who said it. Yes, Ford actually said it. Yeah. Thank you.
Thank you, Pepe. I think we have time for maybe one question. Any question in the audience? Over there.
Very nice talk.
Thank you.
2 points. Of course, your provocative statement about the uselessness in due time of astronomers begs to give a response to that. So that first, I think you already answered it also in your slide, right? In your last slide. Indeed, what I see is that it will be very nice that machine learning can make all kinds of selections in feature space, and then it's up to the astronomers to make chocolate out of it, what that means physically. And so instead of writing proposals to get all kinds of PhD students to do things, we can actually employ the machine learning and get the result overnight because it works 24 hours a day.
And let's stop mobbing PhD students, right?
No, you're right about that one. The other one, more to the point, is right now you're at the phase that you start at catalog space and then do your experiments for fuzzy machine learning. Yeah. I guess that the obvious next one is that you don't use the catalogs because that's a human-informed selection out of the data. So how do you foresee that next steps going to the pixel data
There
itself?
is only one answer: deep learning is what we are beginning to experiment right now. Kai is also beginning to experiment. I think that most answers will come out of deep learning.
Okay.
By the way, about the astronomers, did you read the Hitchhiker's Guide to the Galaxy? The answer is 42. You know, people in the room will understand what I mean, at least the older part of the crowd. Yeah, we'll have, astronomers basically will be freed by all the boring part of the work. That's the point. And they will concentrate on real things. Oh, sorry, excuse me. There is no time, I'm afraid.
Thank you. We're running out of time.
Thank you very much.
So if you could hold that question for the coffee break, that would be great. So now we have Kai Polsterer. Please come ahead.
I think it's fine. Muchas gracias. Yeah, see. So, good morning, everyone, and it's great to see so many people after such a gorgeous conference dinner. Thanks to the organizers. So, I'm afraid in that room are too many people upset of seeing pink posters. So I was recommended not to present a pink poster again. They asked me, wouldn't you consider handing in a talk? So I thought, yeah, what could I talk about? It's definitely astroinformatics and what we do in the regime. And yeah, don't be afraid, as it's always, we need a word cloud, but I'm not using all the buzzwords. I thought a good way to exactly show what we are doing in astroinformatics, and please excuse my voice, was a little bit too late and everyone is somehow ill here. So I'm not using those buzzwords. I thought it's much better to present actually what is done in astroinformatics by showing real science experiments we did, by presenting work we already presented here at ADAS. So I split it in two examples in principle. One example is on dimensionality reduction as a very powerful tool. The idea of dimensionality reduction is in principle, oh, no, the battery is dying. The idea is, I'm not falling down, in principle, to go from a d-dimensional space to a lower dimensional space, n, and preserve similarities in the high-dimensional space by doing the embedding in the lower-dimensional space. And what it is really good for, it helps us to deal with complex shapes. So human pattern recognition is something we are all interested in. And I'm interested in using neural networks. In this case, I used a very cute neural network in a still untrained state. It's my daughter Eva at the age of 3, not trained at that simple brick game. But it's an example that shows what we somehow do wrong in astrophysics. Because I gave her a very simple brick, look at it, and a very simple task, put it in, and guess what happened? Of course, I added a bias, and yeah, it was the second try. The first one didn't. And look what happened. If you give her a brick with 3 squares on it and 2 triangles, it fits in better there. When we do our crowdsourcing experiment, we force people to think into categorizations we come up with. We don't allow them to be creative. And it's an evil daddy who tells his daughter, put the brick in there. But that's what we actually do. We enforce the usage of categorizations. We enforce everyone to think in certain categories, and that's not true. Depending on your scientific use case, you might think of using different categories. And what it is good for is, we presented those things at ADAS in the past. We presented in 2011 something where we used galaxies in the optical from Sloan, and wanted to learn what are usual shapes of galaxies, and wanted to learn what is the embedding, what is included on all the galaxies within there. And then a pink poster in 2014 in Calgary, we presented a method where we wanted to have something rotation invariant. We tried clever stuff, slicing circles, using a Fourier transform on them, mesh representations. We tried a lot of things, but in the end, the brute force approach based on GPUs turned out to be really, really successful in analyzing these data sets. And yeah, why do you do it? In principle, you end up with a large map of prototypes. You end up with a very compact representation of your data set. In this example, those are all the galaxies from Radio Galaxy Zoo. 200,000 galaxies in one simple plot. And you can look at them, and you can inspect it in detail. And what you can do as an expert, come up with your scientific use case, start annotating certain regions, you explore what is in the data. In the next step, you transfer it to all the objects, and this simple circle in the lower left corner for single compact objects excludes 60% of the objects. Otherwise, you were looking at 120,000 boring point sources. This simplifies it. What's even cooler is you can start to discover what is in your data. By looking at the distribution with respect to the distance to the prototypes, you figure out the majority is well represented. But there is a long tail of outliers. Those outliers are the few hundred objects you actually want to inspect manually, and you want to learn about what's going on in the regime. Those are the interesting ones, not the boring general stuff. You can go even further. In this example, I'm using HR diagrams of stellar clusters in the Magellanic Cloud. Without doing any isochrone fitting, I just order them in some sense. Then the question is, what is it good for? Absolutely nothing. Until you put a color bar on top of it. In this case, it's red and green. Please apologize. I know it's not color friendly, what I do, but you end up with a color bar. And if you go back to the spatial domain, you see the distribution of ages with respect to what you ordered in the Magellanic Cloud. So that helps you doing the physical analysis, what's actually in the data. You can go further, spectral data cubes, H1 data. Instead of showing the integral flux for each individual pixel for the spectra there, you learn the shapes and come with a nice colorful representation for the shapes and use this nice representation to overplot what you actually have. And look there, you see arcs, you see the Milky Way on the left-hand side. It becomes much more telling than it actually is when just integrating the fluxes. Color is now representing shape, not intensity. And you can go further, you can show how much is it differing from actually what you are showing, and that shows you where turbulent areas with complex object not well represented. You can go to the time domain, use dimensionality reduction. In this example, we used an echo-state network, a kind of neural network to represent time series, and the autoencoder to project it to lower dimensions. And once you start overplotting physical properties like metallicity, temperature, or surface gravity, you find out that the cool objects that have a low surface gravity cluster in one corner. And that's just showing that there's a certain pseudo-periodic temporal behavior found for red giants. So another example is regression problems. And in principle, I could skip the slides, thanks to the great introduction by Pepper. In this example, you just go from the D-dimensional space to a one-dimensional space. You just want to find a value for something. That can be photometric redshift, could be starburst ratio, metallicity, a lot of parameters you could estimate in that way. And what we presented in 2011 was, how well can we predict outside of our sample, comparing local versus global regression models. In 2013, we presented the work on feature selection, where we at a certain point thought, now just do brute force stupid test on all the features, and came up with very powerful new features that improve performance tremendously. In 2016, we presented something on how to actually evaluate and properly score probability density function. If you don't want to make point estimates, if you want to have probabilities, PDFs being predicted, you need proper scores to do it. The lessons we learned from all the things we presented back then were the features we currently store in our catalogs are perfect for humans, but are not the best, actually, if we want to do machine learning. We go from a complex image to single values. So what we did, complex images means you have to do deep convolutional networks, deep learning, and we combined, in this example, a simple deep convolutional architecture with a mixer density network, predicting a mixture of Gaussians in order to have a probability density function, used a proper score as loss function when training, and we're able to predict, very colorful again, the probability density distributions for individual objects. And being able to predict multimodalities helps you to deal with the degeneracies in your catalogs. Some objects might have a redshift of 0.7 and also a probability of having a redshift of 1.4. And this is tremendously important to deal with the tricky objects that are not well covered by the available data. So astroinformatics is definitely more than just analyzing complex data. It's covering a wide range, not just pink posters, but it's also covering visualization aspects. We have so many great talks here at ADAS all the years with respect to all the problems we are facing. It's about visualization, it's about infrastructure. How do we store data? How do we access data? How do we make it accessible in the sense of running our code next to the data? So, and slowly coming to the conclusion, what is astroinformatics? Is it really something new, or is it business as usual? So Andreas gave a really nice talk yesterday how the data centers evolved over time. So in the beginning there was a sky, and we were watching the sky for, I guess, several 10,000 years, and we were doing our analysis with a naked eye. At a certain point, we started to build telescopes, smaller ones, larger ones, and used them to improve our ability to see what's happening in the sky. Later on, dedicated instruments came up to allow us to see things we couldn't easily see with our eye and to understand the physical details in more facets. After the introduction of the detector, being photographic plates being replaced by CCDs, we got into the digital age. Everything became digitized and everything became computer processable. So the data went directly from the sky, through the telescope, the instrument, the detector, into computer, into huge data warehouses, storages. The service providers nowadays providing those archives, they are a new way of accessing those data sets. And of course, computers nowadays used for simulations are another source of rich information, allowing us to test our physical hypothesis. And now, just going further on top of that, you now put machine learning and artificial intelligence. And from my perspective, I would say we are covering, starting from the detector, everything until the knowledge, but it's also involved in telescope. We have seen great talks, software-defined telescopes, LOFA, what a great machinery of discovery. Instrumentations becoming more and more computer-controlled. And in principle, I would say, It's everything after the detector. And the ADAS conference is well in scope what astroinformatics is about. I would say astroinformatics is the way we get from data to knowledge. And the last 3 seconds I use to use my proper native language. I think it's Konferenzterminankündigung, I would say in German, but actually it's announcing the date of an upcoming conference. So whoever is interested in astroinformatics, next year astroinformatics is happening in Heidelberg, and I would be happy to see some of you. Thanks.
So we have a couple of minutes for questions. Any question? Yeah?
I have a feeling that when we try to apply machine learning methods to actual data, not a very finely curated collection of spectra that have been background subtracted, redshifted, etc. When you try to apply these methods to the data that exists in the archives, what we find is that the great heterogeneity and difference in the quality of the different data sets essentially makes the algorithms find more the difference in the quality of the data sets than rather the information contents inside of it. What's your experience about that?
Of course, it's not a magic black tool, a black box where you put in data and you get out a publication. Fiddling with data, getting your data in the right shape is one aspect of doing this kind of research. But the other aspect of research, if you properly take into account the uncertainties and propagate them correctly and have algorithms capable of dealing with those uncertainties, those objects are very uncertain due to their measurements. In principle, they can be anything, but with a low likelihood. And for that reason, it really depends on how you actually treat the results in the end. So I think you are absolutely right. Currently, it's hard to get a data set you can run it on, and on the other hand, it's hard actually to find algorithms properly treating your uncertainties and propagating them. That's at least my experience on that field.
But would you say from applying these algorithms that errors in the current existing data sets we have are properly done?
So for a lot of things in the data set, I would prefer, instead of having an empirically found error measure and saying this is a magnitude with an extra error, I would be happy to get a likelihood function out, to have a probability density function out, deblended or blended, not being a flag, but being a change in the probability of having a certain magnitude, having a higher probability of being blended to be actually lower at a certain point, and being reflected in a proper description in the probability space to process that kind of data. That's what I would prefer, but we just need a few more years, and I bet you will provide something like that.
Okay, any more questions? Okay, so let's thank Kai again. Now we have Joshua Peak talking about convolutional neural networks.
All right.
Trying to get one.
I'll just yell, wave my hands. Check, check. Hello? Excellent. Hi, my name's Josh Peak. Oh, all set? Oh, we got a new laser? Amazing. Oh, that's not what I want on the screen. Oh, yeah, okay. Cool. Right. Ignore all of this. Great. Hi, my name's Josh Peak. I'm from Space Telescope Science Institute in MAST. I'm going to be presenting some work I've done in part with Craig Jones, Jonathan Hargis, and Rick White. And speaking of Rick White, it's good time as any to announce that I'm taking over the PI ship of MAST. So watch this space for gray hair appearing next to ADAS. All right, on to convolutional neural networks. So we need tools to deal with raw pixel data. It's a real missing piece in astronomy. What you're seeing here is images of the cosmic web, the surface of the sun, the interstellar medium in a galaxy, and very few of our tools are able to handle these kinds of images generically. You know, if you apply our normal tools to this, you'll find all the stars, but this structure is very, very hard to find. So we need tools that are gonna be able to take in these pixel level data and use them. I've written personally tools that can deal with finding, you know, individual filaments here or individual linear features, but then they're not very useful here or here. You want something more generic. So I'm going to argue that neural networks might be a useful tool for that. I'm going to try to give an extremely brief overview of neural networks as I move forward, and then review a bit of the convolutional neural network literature. So imagine you've got two points, an x and a y, a mass and a color, for instance. You might feed these through some kind of network. So the way this network might work is you have a bunch of weights. So here I've labeled my weights W11, W21, et cetera. And they get summed up. That sum gets passed through some kind of function. It's called an activation function. It's typically increasing and monotonic. This whole structure here is typically referred to as a neuron. Now you go to the next level, there's some other level of weights. You could imagine many of these levels going to many neurons, but I'm gonna skip the intermediate steps. And then you might have some final parameter here. So maybe the idea would be is you would feed in a bunch of data about, say, cats and dogs, and their mass and their colors. I don't know much about cats and dogs. Over time, you'd be able to change these weights so that whenever you put in the mass and the color of a dog, you would get a result that signaled dog. And if you put in the mass and the color of a cat, you'd get something that signaled cat. This particular network probably wouldn't work very well. The idea is that you build these networks deeper and deeper. So if you've ever heard of deep learning, what they're talking about is the depth of the network. So you might have maybe many more inputs than I talked about before, and then you'd have these various hidden layers. So this is the sum and the function all together, and then getting out some kind of labels at the end. So cat, dog, giraffe, et cetera. The problem with these kind of networks, they're very useful, but one problem for imaging is that images are large. So if each one of these things is not a weight or a color, but rather the value of an individual pixel, think of a small image. It might be 100 pixels on a side. So now you've got 2 pixels, you've got 2 sides to your image, so you've got 10,000 pixels. Now, if you want to connect this to this, that goes like the square because each one connects to each one in these kinds of deep networks. There we go. And so the number of weights scales as the number of neuron squares times the number of layers of depth. So you can end up easily with billions and billions of weights. You're now trying to train all of these weights to make these networks work, and this would take infinite time. So enter convolutional networks. Deep convolutional neural networks are designed to work with images. And I have a lot of trouble explaining them to you, so I'm going to show you a little video that I really like from a website that gives you a nice interactive. So if you just type interactive convolutional neural networks into the laptops you might have open, you can play along with me. Down here you have an image, and each one of these little colored bands represents those weights, those trained weights we were talking about. So what you do is you provide different convolutions. So these are actually all the same. You see it's the same colors going to each pixel. That's convolving this image into this. The next layer, you sort of average these pixels together to make the images smaller. It's called a pooling layer. And then you might do another layer of convolutions where you take these convolved images and convolve them again. So you've got another layer of convolution that's happening. And you can see that the colors are all the same. So each convolution is happening many times. Now you have another pooling step, and then this layer is what's called a fully connected layer. Like we saw before, every pixel, every neuron is connected to every other neuron. You have another layer like that, and then you have a final output layer here, which might tell you what you're actually looking for. So these are the labels, and here we're looking for numbers. So if I draw the number 3, the 3 goes in here. It's convolved many times. You have this layer of pooling. And then these convolutions are then convolved in these very many complicated layers where things start to not really be visually interpretable. These get pooled again, and then you have a fully connected layer, another fully connected layer, and indeed it comes out with the right answer. You can see there the number 3. Convolutional neural networks are exploding in their use in the astronomical literature. We have a lot of images to deal with, and that's largely where they're being used. They were going up by a factor of 2 every year until this year where they're going up by a factor of 3. So we'll see what happens next year. These are the papers by type. Strong here is strong lensing, a lot of interest in strong lensing. Studies of the solar surface, time domain, diffuse structures, particle physics, galaxies, artifacts. There's lots of different things they're useful for, and I'll talk about a couple of these papers. I did a quick analysis of all these papers. These papers claim to be faster, so they're faster than any previous technique, or at least what they consider the state of the art in doing whatever task they were trying to do. And these claim to be better. i.e. they're having a better recovery of the answer that they're looking for in any of these subdomains. So that's about 11 papers that claim to be beating the state of the art even after such a short time being used in the astronomical literature. I'm just going to show you a couple of examples. Galaxy morphology was really the quotes, starting gun for Astro CNNs. And this was started because there was a competition to try to reproduce the morphologies that had been selected by citizen science volunteers in the Galaxy Zoo project. And these competitions are actually really important, I've found, in really getting people excited about a particular tool. Convolutional neural networks themselves were sort of selected by the computer vision community that way, and that's why these become exciting in astronomy, is they won this competition. The way this was done by Dielman et al. Was to select pieces of images and do this, this step here to make basically 16 images from every galaxy to avoid the problem that convolutional neural networks have, which is not understanding symmetry. So this basically imposes symmetry on the problem. Then a big network is built, and you can see these are the layers, the activations of the layers as you put in this spiral galaxy. So this is the convolutional layer, pooling, convolution, pooling, and so forth, like I showed in the previous image. It's really good at telling different kinds of galaxies apart. But CNNs can work on much more interesting problems, I think, than just reproducing what humans can do clicking on the web. They can also extract shape information from weak lensing maps. So if you take a weak lensing survey, typically what people will do is compute what's called a two-point function, a relatively simple statistic on the image. And when you do that, you get this sort of banana shape in measuring something like omega matter versus sigma 8, which is to say that it's very confused about different kinds of universes that have these different parameters. What these folks did was took 5 different universes along this banana shape that are confusing to the two-point function and made these 4 images of these weak lensing convergence maps. You feed that through a convolutional network and it can tell them apart quite accurately. There's a huge amount of information in the image plane in shapes that is not computed by something like the two-point function. That's a critical idea that I think is really important in convolutional nets. CNNs are also really, really good at classifying artifacts, which turns out to be very important. So an artifact in the LIGO data is defined as anything that triggers LIGO but does not give you a Nobel Prize. There's all these different kinds of artifacts. These different kinds of artifacts were fed to, again, citizen scientists who were classifying them. And so the question was, could we do better and faster than the citizen scientists in classifying these artifacts? In fact, working live on the stream. And these folks were really good at doing that. And here's what their confusion matrix looks like. So if you feed in one kind of artifact, what does it recover? Most of the time, it recovers the kind of artifact that you're looking for. So this is a really nice result. You can see places where it doesn't do perfectly. But a lot of places, it's doing almost 100% accuracy at recovering the kind of artifact that you put in by just putting in an image, a spectrographic image of the artifact. So transfer learning, which I'm going to talk about for the rest of the talk, is a really neat idea that has been proven very, very effective. So I'm going to talk about the exact same topic, these same LIGO glitches that were used to train on. This second group, George 2017, used a network that was trained on ImageNet. So ImageNet is 1 million images or so with 1,000 categorizations of terrestrial things. So, you know, is it a wheel? Is it a starfish? Is it my face? What is it? So that exists on the internet. People have written networks, huge, very powerful 50-layer deep networks, and already trained them on these images. And what George et al. Showed was if you took these networks and added a few extra layers to the bottom, and then just trained those layers on these glitch images. So you send the glitch image through the very top. This image is expecting something like a starfish. But at the very end, you train just a few layers. You can train in 2 minutes on a laptop something that will actually do even better than the previous paper. So this is the same diagonalization matrix. And you can see the numbers here are like 300 and the numbers here are like 1, which is to say it's extremely good at recovering the right answer. So this is really cool. It shows you that networks, convolutional nets that were trained on other things can be used for astronomical purposes, which is great for us because these networks are very expensive to train, take a long time, and a huge amount of expertise. But I think the really exciting thing is that that you can do unsupervised learning. So the last 2 talks briefly mentioned how important unsupervised learning is. And this is, I think, a really nice example. So what they did was they then took that same network that they had trained. So you had this big network that somebody else had trained. You had a bottom couple of layers that were there to train for these LIGO glitches. And then they removed some of the layers that they had trained and ended up with these feature vectors that didn't have any meaning. So you can imagine these networks go down and down and down until they classify your few last glitches. You go 1 layer up, there's a feature vector there. So when you put in your image, it lights up these neurons with some values, but you don't really know what those mean. You can feed those vectors into some kind of clustering algorithm. Here they're using what's called t-SNE, it doesn't really matter. And what you find is that these vectors then recover what you saw before. So these are the blip glitches, and these are the extremely loud glitches, and these are the none of the above glitches. But I think this is really exciting. If you look at none of the above, you can see it actually breaks up into a number of subgroups. And if you plot those subgroups, what you find is that it's actually figured out that these are a class and these are a class. So that it's doing this artifact clustering in an unsupervised way. I want to tell you a little bit about what we've been doing for doing transfer learning for image discovery in MAST. What we've done is we've taken an image. This is just a test image here. We're using the Carina Nebula. We've cut it up into little pieces. And we've fed it through one of these pre-trained existing networks, okay? So now for each one of these images, I can say, oh, well, this image is obviously 10% velvet and 8.2% binder and 6.4% gene and so forth, which of course is meaningless. But if you then feed this vector, this 1,000-dimensional vector, saying what kind of terrestrial images it is, and you cluster them, you end up with a map that looks like this. And this is a result from, again, from t-SNE using the same clustering algorithm. What does this mean? I'll show you. On the right side, I've just selected one point in the t-SNE space and chosen all the things near it in that space. On the left side, we've got this red box, and the red box is showing the exact same thing as the red point, but in the image space. And you can see that this is doing a good job finding the surfaces, the lit up surfaces of this photo dissociation region. If we choose another region in this same map, you can find the saturated stars. You choose another region in this map, you can find these faint blue wispy ionized features. So I think this is a really good example of something that could be very powerful in an archive and something we're going to be pursuing. We feed all of, say, Hubble's data to this, and we say, please show me images that look like photodissociation regions. Can it find more? I just wanted to say I've done a lot of this work with Deep Skies Lab, which is mostly just a little Slack channel. We've all been chatting. This is with Brian Nord and Camille Avestros. So you should feel free to join us if this stuff is exciting to you. It's a place where a lot of real deep learning people hang out who know a lot more about it than I do. And I'll just leave you with my conclusions. And thank you.
Any questions?
Hi, I have two questions. The first one is, which is the preferred technique for training neural networks at this point for astrophysics? And the second one is, what's the order of magnitude of training images that we require for arriving to the results you just presented?
So the preferred, at least for me, the preferred software right now is called Keras. It sits as a layer on top of TensorFlow. What's nice about it is it really makes things simple. So I've trained a bunch of different networks for a bunch of different things, but many of them, the actual network is maybe only 20 lines long, very straightforward, and examples abound, and there's a big community for it. I tried doing this 2 years ago with something like Caffe, and it was, even installing Caffe was a huge amount of work. The results I just showed didn't require any training at all. All that was needed was clustering. So we fed the images in to existing networks. You can download the networks, they already exist. And then we did clustering on the results. So sometimes these networks take a long time to train. If they're arbitrarily complex, they can take arbitrarily long time. But I think there's a lot that can be done without a huge amount of GPU power.
It's already me.
Oops, sorry.
There is already me. I already have the microphone. So, okay. Is there any way or any attempt to your knowledge to attribute a probability of, for an attribution of a structure to a specific class?
You mean in this last example I was
Yeah,
showing?
for instance, I mean, the probability that a given structure belongs to a given class.
We don't have a definition of class, so the problem is ill-posed. I haven't told it anything about classes. It's as you know, an unsupervised problem. So there isn't a class, and as you know from t-SNE, there's no sense of class here. So there's no list, there's no finite number of objects. So I can't tell you, I don't even know how I would answer the question.
So basically you cannot attribute an error.
I wouldn't even know upon what the error would be attributed.
Okay.
Okay, so deep learning became really famous using these terrestrial annotated data sets.
Yes.
Okay? So, but in astronomy, well, we have a lot of data, but it seems that we are still missing annotated data in astronomy. Well, in the sense that galaxies was really popular, it was successful, but it still is only one or two, maybe, big annotated data sets in astronomy. So do you think we're still missing?
Yeah, so I'm professionally an interstellar medium astronomer, and I'm not even sure what it would mean to have annotated data in the interstellar medium. It's largely a continuum, it's a fluid, it's a field. And so, yes, it's extremely frustrating to me, but it's almost as frustrating to me when people try to annotate the data and say, well, there's 19 filaments in this image, but not 17. Like, no, that's not how the universe works. And so it's a struggle, I think. I think there are certainly places where annotation is helpful, but it is surprising. I mean, citizen scientists were willing to go through glitches in LIGO data. So annotation engines exist.
I guess I'm a little concerned about yet another wave of overhyping of all this technology. Because in a lot of astronomy, we have sufficient statistics for what we're doing, very, very close. Certainly for extragalactic. So the reason why you can use small numbers of parameters to describe extragalactic fields extremely well, including the photo-Z classifiers we're looking at,
I agree.
is because we've extracted almost all the information into a very small number of numbers. So I think these convolutional networks are very exciting for things like Carina images. If you actually care about the interstellar medium, Bruce Strain will be all excited. But whether we can ever make statistical models based on these, I'm very doubtful about. Somebody said, give me the n-dimensional PDF of the Audi Blender. That's fine if you have a model for it. But if we go towards the network, the deep learning approach, I don't think we're going to have models. And I'm not sure that the statistical backing of the measurements we're making is going to make sense. So do you really think, I mean, to what extent, and this is another example. Here we know it's a two-point correlation function, but it's a pure Gaussian field. You're finding something that's not in the astrophysics.
No, it's not a pure Gaussian field. This is a problem, actually. What's happened is the CMB culture has come into the low redshift universe and said things like, oh, it's a random Gaussian field, all I need to do is run a two-point function. Well, this is factually wrong. At redshift 1, there's all sorts of nonlinear things happening, and we know it's very clear that there's highly nonlinear physics going on here. So that's why the high point, the 3 sigma peaks are very important, and that's why the same situation is very important. So I very strongly disagree with that.
No, but no, let me finish that then, which is that you plotted omega m versus sigma 8. The information in that is totally in the two-point function, right? So the other things you're discovering about other aspects of the astrophysics.
No.
So I'm just concerned about the interpretability. I mean, I'd like a comment on how we're going to actually interpret the results of these machine learning.
So there are so many things to answer that question. One of them is, I do think the places where this is important is where you have complex nonlinear fields. I don't think you should apply this to the CMB. I'm not super hyped about using it for your faint fuzzies. I don't think that's very interesting because pretty much it's going to be encapsulated by the Sirsic index and 3 other numbers. So I don't think it's applicable. I don't think convnets are very useful when you're working on things that are pretty much point sources or pretty much described by linear physics. But I'd just like to point out that 7/8 of the baryons in the universe are in a nonlinear state. They're not in compact objects. They're in the diffuse fields, and we're getting better and better at imaging those diffuse fields. And we're going to be hit with this problem that the entire universe pretty much looks like that. And as we get more and more of those data, we have no mechanism for dealing with these data. So I'm not telling you that we should no longer do point source photometry and that everything should be neural networks. What I'm telling you is that for images like this that sit along the halls of Space Telescope Science Institute, we have no machines to deal with them. And that's what I'm hoping to provide.
I think this would be a great topic for the BOF this afternoon.
I agree.
Yeah, so I would be happy to have you guys there. Okay, so let's thank Josh again. Now we have Alejandro Barrientos, who's talking about machine learning approaches for detection and classification of astrochemical spectral lines.
Everybody hear me? Okay, now we're fine. Okay, let's start. Hello, everyone. My name is Alejandro Barrientos. I work at the Joint ALMA Observatory, and I'm also a PhD student in the Federico Santa Maria Technical University. And I would like to talk about today is machine learning approaches for the detection and classification of astrochemical spectral lines. So a quick agenda for today's talk. I'm going to talk about an introduction, then to talk about the domain complexities of this field, a little bit of state of the art, and then go to the actual objectives and to conclude with some of the research progress that we have done, and then talk about the next steps and some final conclusions. So this talk is actually intended for the non-experienced. I know that there are several students in the audience, so I wanted to give this talk to motivate them to join the field. Talking about a little bit of history of the detections in space, they started about the late 1930s with the work of Swings and Rosenfeld. But until today, the last time I checked, there were around 250 molecules detected in space, whether in interstellar medium or extragalactic sources. To be able to detect these molecules is a pretty hard job. Why is that? Because there are many, many complexities that have to be considered, and I would like to classify them in two major groups. One of them has to do with the source complexities, and in here we see things that are related to the source itself, such as the temperature, optical depth, and abundance, and so forth, kinematics and pressure. And then we have the other group that have to do with the complexities that have to do at the molecular level, such as the molecular vibrations, electronic transitions, rotations, and frequency. You can see the little guys over there dancing at the song of their transitions. And there are also some other factors, such as the line shape, and also that the literature is always in constant evolution, so you need to keep up to date. So some of the state-of-the-art that we have found, there are many applications that are already in the open that you can use to do some line analysis and then to try to obtain some of these lines, spectral lines. You can see them here. And there are also some more approaches, such as I remember an undergraduate thesis from Nicolas Miranda, from which I took some concepts also for this work. And there are also some applications that are already existing to do machine learning classification, but they are done using spectra from elements here on Earth, in laboratory spectra. So they don't include any of the complexities that you have in space. So now that we have established, well, that there are two interesting problems. One of them is to be able to take a data cube and then extract the interesting emission regions. And for those regions, well, you would like to do a classification of the spectra in those regions, hoping to find some molecular species. As I mentioned, this task is quite difficult. And that's what we would like to try. So what we have done so far, what we have done is in the area of detection of regions of interest, what we have done is to take a data mining technique which is called DV-scan, that can be used to find clusters. So what we have done is to take, let's for instance, one of these FITS files, from ALMA, and we compressed the FITS file across the frequency range to obtain a moment zero image. And from there, we basically took a slice and we kept all the emission which was above 3 sigma. And we got basically this region. And then we run the algorithm to obtain the clusters. We found 3 clusters plus a noise point.
And for each one of those clusters, we generated a spectrum by adding the intensities of all the pixels in the given region across the frequency range. One of the pros of using, advantages of using this method is that you can find clusters in irregular shapes, which is different from the traditional clustering algorithms like k-means. But the disadvantages of using this is that this is very sensitive to the parameter selection, so we need to find a way to do this a little bit more automatic. And also, when we do the compact of the cube, if you have regions of low emission, they basically got lost in the noise. So now moving to machine learning approaches, we tried two very popular machine learning algorithms. One of them is artificial neural networks, and the other one is support vector machines. Why we chose these is because they were, well, very popular at the time, and they have very good generalization capabilities. So I would like to acknowledge the work of these people who I work with. And in order to do the training, we took the code from ADMIT, from Peter Teuben, and we did a slight modification to generate some training examples. And also, we decided to do a selection of species and transitions from ALMA band 6. We only used one band because in this band we had 64 gigahertz of difference, and hence we had about 640,000 features because we did basically one feature per, per frequency. And this is an example. This one here is the training example that we generated. And this one here is basically the moment zero of one of the ALMA FITS cubes that we took. And this is, if we do the spectral lines, we can see them here, the real ones. So the results for this, well, in order to process this, we selected a software library that is called PyBrain, and we created a feed-forward neural network with a sigmoidal activation function. And then we did the training with backpropagation until it converged. This took about 30 minutes for 15 examples per transition. And we used the mean error squared as our error measurement. And we can see when we tested this with 4 different real-world FITS files, we obtained a probability of belonging to the class about between 76.9 and 94.09%. And in all the examples, the spectra was correctly classified. Okay, now using the support vector machines, which was another technique, we decided to go for the 1 versus 1 multi-classification approach. So you either belong to a class or you don't. It's a binary classification algorithm, so it does not allow overlap. We started testing with using libsvm GPU library to take use of our graphic cards in the laptop. However, this library did not support the probability output that we required in order to compare it to the previous experiment, so we had to move to scikit-learn. We used 200 training examples per transition, and the training only took 5 minutes, which was pretty fast. However, whenever we wanted to increase the number of examples to 400, we had an overfitting, so basically the results were not better than using 200. And you can see here that for the probabilities, well, they're actually just a little better than random. It wasn't very good, and we correctly classified in 3 out of 4, which is 75%, so it's not that good. Okay, so we also want to do this a little bit faster, so we tried some parallelization experiments. We used MP4Py library to try to process the regions of interest a little bit faster. And we got a speed up of 2.28, which was about twice as fast. However, we we did a kind of shameful parallelization because we basically processed more files, so we didn't actually separate the cubes. So shame. So what are the next steps? The next steps are that we wanted to try another approach. This time, we selected some techniques coming from the text mining field, which is called mixed membership models with Marcelo Mendoza, and the publication was already accepted for the International Conference for Pattern Recognition. And we use something called labeled latent dirichlet allocation algorithm, which basically is an algorithm that allows us to find the hidden structure of the data in order to extract topics from the data. So we did an analogy. In this case, whenever we use topics for text, in this case we were molecular species. And for words, words in the text, we use transitions. And the term frequency, how many times a word repeats in a text, the analogy was the energy of the transition. In this case, the energy in temperature in Kelvin degrees. We created the vocabulary using Splatalog, using about 1.6 million records. And since Splatalog has 7 filters, depending on different physical conditions, we use 7 models. It was implemented using Mylod's labeled LDA extension for a library called JGive LDA, which is pretty popular in text mining. And we are currently testing this using real-world examples, but our initial test suggests that this is feasible, so we're very excited about it. And when this is a little bit more elaborate, we would like to add some restrictions and also show astronomer knowledge into the model. And finally, we would like to build a catalog by analyzing all the public data from the ALMA archive and then having that available for the astronomers. In conclusions, well, this is a pretty hard problem to classify and to find the astronomical spectra. There are too many physical factors. In the initial test, we only consider frequency and high emission, but we are testing some other techniques in the machine learning world. And well, the mixed membership models suggest that this approach looks promising and we need to keep going. The region of interest detection technique has this problem that does not allow us to find regions with low emission, but we need to try some other techniques. Thank you.
So I think we have space for just one question.
Thanks for your talk, Alejandro. My question's about varying noise. Can you say something about how these new techniques that you're working on, how they deal with varying noise as you go through the cube?
Yeah, well, one of the good things about, one of the latest techniques that we're testing, it is very robust to noise. When you do the training, you can add some noise, and then the algorithm will be able to adapt to the noise. So it's one of the things that it is powerful with the mixed membership models algorithm. So it is a generative approach, and therefore it already assumes that you will have noise in the data. So it's basically designed to support noise.
Okay, so let's thank Mauricio again. And finally, we have Hossein Teimourinia. Did I pronounce that correctly? Teimourinia? Cool. So, please.
This is in the folder. In the folder. The first one, yes, go to it, and this is the first one. The first. Okay, this should be this. Okay, and 11. Okay. Thank you. Which one is this laser? Which one is laser? Laser. Laser is this. Thank you. Okay. What I'm going to present today is about application of machine learning methods in the CD80's advanced search service. Long story short, it is an image classification, but it's a little bit different from the methods that, like CNN, when we want to extract features, we use a new method. I'm going to describe this method in detail. When we are talking about astronomical images, we are talking about images that are very complex in terms of size. They can be taken from different instruments, in different filters, different regions, and ultimately all of these images collaborated and then stored in different data centers. In order to get this data in these images, we have to go to web page of a data center like CADC. When you are going to search for a set of images in CADC archive search, you have to select some options, like, for example, bands optical, different instrument if you want, in different filters. And as soon as you press the search, you will end up with this page. This is download page. Our available images can be appear here. So here there are different filters. You can do some filtering here, for example, in terms of coordinates, time, and different parameters. You can select what you want here, and then download. Here, the data can be selected only based on metadata, but we are going to add another filtering by machine learning in this page. Suppose that you are not using machine learning yet. When you download, press the download, you will see a page something like this. And before downloading, you don't know which one is good image, which one is not. We are going to address this question: which image is good for astronomers for doing photometry? This is the question we are going to address with machine learning. So if you don't know what are you looking for, and you want to download something, you will end up with this, for example. This image here, you can see some pattern there, but it is garbage. It cannot be. It is not important for astronomers. It cannot be used for photometry, and people don't want to see in the download something like this. If you go to this and see this image, this is some warning, saturated, some cosmic defect on it, and some fluctuation because of the big and extended object. So the photometry can be done, but with caution. The upper images are not bad. So we are going to give a number to these images before downloading, and people know before downloading that they are going to download which image. Even if you know, even if you know what are you looking for example this, and you are going to do photometry on this object, for example, if you select, you can see that you have 3 images. Before downloading, you have 3 addresses, and you don't know which one is good. And here, as cosmic defect here. Here is not bad. It seems it's not bad. And here it's so-so. So we are going to separate and classify them and give a number before downloading. Okay, we are going to do that with neural network. We are classifying the images into 4 different classes. This is what we want. And on the left, what we have. What we want, what we have, we can connect this information together with a neural network, very highly interconnected system. If we have good information on the left-hand side, then we can do some machine learning things. How we obtain the useful information? We can do CNN, but we did. But we chose another approach that is more familiar for astronomers. We extract our features by Sextractor. Sextractor is a very popular software that can give you very useful information of the objects in an image. For example, how big an object is, the extension, the size, or for example, the luminosity, the brightness, the number of detected images, and the fluctuation in the sky that are very important parameter for astronomers. When you give an image to Sextractor, you will end up with a table. The table has very useful information, but is not suitable for machine. We have to change it into some different form. What we have done, we changed the information of Sextractor to a fingerprint, something like that. And this fingerprint is something like this for 3 images. For example, in the blue one, you can see the image should have very populated because the size is the number of detected objects, very populated one. And no fluctuation in background. And compared to the other, not very extended. It is a size. These 3 parameters is related to size. And this is the flux, not very bright. So I can conclude that it is a very populated image with no fluctuation, small objects, and faint objects. If you go to see the red one, moderately populated, very bright object should be found there. With high fluctuation is a sign of contamination, and very bright. And if you go to see and the green one, it is intermediate. This is the result. In fact, if somebody is given 10 different fingerprints, and when he or she played with this fingerprint, she or he can understand which one is which. So we can give this fingerprint to machine to do classification for us. Okay. We created about 2,000 fingerprints for neural networks and classified these to 4 different classes. Even in this step, you can use this information and use unsupervised method like Cohen method to separate things from each other. So we trained a network, and when you train a network, when you connect what you have and what you want by a network, in fact, you are creating a hyperspace that you are going to find the minimum point of this hyperspace. Why? Because we want to minimize the distance between what we want and what we can predict. So, for example, if we were very lucky and find a very good method, we can go and find very easily the minimum, and we have a trained network. If we are not very lucky, with maybe in initialization step, we end up with this method. I think yeah. Go. Yeah. Okay. It goes to local minimum, so it is not good point. So with different methods like a stochastic gradient descent with momentum, like this, we can end up with better result, and we test to make sure that we are in the best position. When we make sure that everything is good with our network, we have a trained network, that this trained network can accept a new fingerprint of an image and give you a probability. So this image, new image, most likely belongs to class 1. Okay, what is our classes? Certainly we want to separate garbage. This is one class. The second class is high fluctuation with bright objects, contamination. We would like to warn astronomers if this image has contaminant object. In order to find this, we have to make good contrast in our classes. So I added 2 other classes to make this contrast and in different patterns. Low fluctuation and low density with bright objects, and low fluctuations, high density with faint objects. This is some results. The first 100%. Before downloading, you know that you don't want to download this image. And there's a warning for the second image, but here is not bad. You cannot download and work with. We tested different methods like CNN. In the CNN, the first 2, because in the smoothing step, we kill information. The first and second can be confused. So, but in this method, with this fingerprint method, we can separate things. Another thing, when you know what you're looking for, we can give you a set of 3 numbers. We don't have contamination, it is 0. But it is not garbage, it is 0 here, sorry. We have contamination, number for this. Which one is better with low number? This image is better. So people can download this. Instead of it is saving time because you have to download 3 big images otherwise. Okay, this is another example of the final one. 2 images, identical images. Again, you have only 2 addresses to download, but we give you these 2 numbers. No contamination, no garbage, but here we have 100% bright object, low density. Here, faint object, and a small object, and faint and small. Let me to magnify it. This is noise, because a small object and faint mostly is noise, and we don't want to download this. At the end, so we can, it is not necessary user memorize these numbers. We can do on the behind the scene this for the user, and at the end, at the download page, we can present this kind of a slider for each class. We want to have no garbage, we slide to the left. If you want to another, we can put an option here. If you want, say to user, if you want, we can suggest the best image based on the number, or we can present 4 different sliders with small help that people can play with a slider and find the best image for the photometry. Thank you.
Okay, I think we can have one question. Here.
As it is common in astronomy, one man's garbage is another man's signal. So how do you make this applicable to different science cases? So for example, the images that Josh Peak was working with earlier are all background because they're diffuse objects. So I can imagine they would all fall in your number one category. How would your algorithm deal with that? Or do you have different settings of the algorithm that would look at images with different scientific content?
Here, at least in this project, we are aimed to separate high fluctuation object that we know information for photometry. This is the goal of this project. With this criteria, we can separate this kind of object. And because we wanted to add more options for the user, we add more, but we selecting better in future that we can extract from Sextractor, we can address the question like this. Thank you.
Okay, so thank you very much. So now it's the coffee break. Remember, if you go downstairs, you'll have more coffee per person. Plus, you get to see some posters.
Welcome back, everyone, to our session. This will be a session continuing on machine learning and astronomical data analysis. I'm Tony Kruger from Space Telescope Science Institute. I have just two quick announcements. One is a public safety announcement. We are asking all the speakers to use the laser pointer and not go to the tactile trying to touch the screen. Yesterday we had a partial fall, today we had a total fall. We like our 8Ss to be memorable, but not in that manner. A second announcement is there were 4 speakers in this session. Josep Ferrer will not be speaking today, so we will have our first 3 speakers, and maybe we'll get to lunch a little bit earlier. Our first speaker is Sebastian Febrero, who will be speaking on stellar parameters with deep learning from CADC.
Hi, everyone. Not Ferreira, but it's a good translation of Fabro in Portuguese, actually. Anyway, so today I'm gonna talk about stellar parameter with deep learning. It's work we've been trying to do since January with a group at the University of Victoria, mostly student and prof over there. So our problem is really nothing new. We have a bunch of data, photometry, spectra, astereososmology, and we want to have estimates of physical parameters. Things that describe the stars, chemical abundances, temperature, surface gravity, rotation turbulence, it could be anything you want. We wanted to keep it small to start, just because, making sure that things work. So we're just gonna focus on spectra and 3 different parameters, temperature, surface gravity, and metallicity. And the reason is this is a well-known problem. I mean, it's been done for the last 20 or 30 years. I guess you have spectra and you want to measure abundances or all those 3 parameters, and then you make those measurement of equivalent width, you do non-least square fitting of a match of stellar atmosphere model grids, or you can do into the projection, or you can do even data-driven model. Something called a Canon has been quite popular lately, when you actually train a model, data-driven model on a previous pipeline, and to get your parameters, and then you can estimate the parameters of the other stars that you're interested in. So we decided, okay, well, let's see what deep learning tells us. And there is a lot of promises of deep learning. There is, a lot of hype, and then saying, also, let's see what's going on. Yes, you can see whether you can discover a puppy or muffin there, and then apparently the machine does better than us. So say, well, that's great. Obviously, a puppy and muffin is a very interesting use case for us. So I say, why not? Let's see what's going on more in a theoretical case, what's going on with the deep learning thing. So we saw early this morning that feature extraction and feature learning it's a pretty hard problem. And deep learning has this promise that it will automatically describe these features for you. And why is it popular now, whether deep learning was invented a long time ago? It's just because we have more compute. So before, if you take this popular plot of accuracy versus the model and the data size, and then neural network has been slowly growing, and this is in the 90s where this was popular, and then there was this desert of machine learning, and now we're back into the hype where apparently neural networks are doing much better than other approaches. We don't exactly understand why, because there's lots of problems with this secondary local minima. So our starting experiment was a few students, a bunch of really great deep learning framework, two 16-core VMs, small thing, no GPUs, and terabyte of this DSS spectra. And previous, distant past machine learning knowledge, which we had to really recover. I'm not going to go into details here. This is really the deep learning typical architecture. It's just, sorry. The inputs are the spectra, the outputs are the stellar parameters, and here we have a bunch of layers of various deep learning. It's this big optimization problem, basically, and the difficult part is there's lots of little tuning parameters, which we call hyperparameters, how many layers you want to put, learning rates, and other things like that. So we ended up by trial and errors and with another method that we'll explain later, using this thing called the StarNet that we claim to be the StarNet, which is basically a convolutional neural network, but for spectra, not for images. So it's a 1D convolutional neural networks, 2 convolutional layers, a max pooling layer, 2 fully connected layers, and an output layer where we get those 3 parameters. So first we tried on simulation. So we have a bunch of matched, bunch of grids coming from the Apogee data sets that are matched really to, those are grids generated to really match the Apogee data set. And these are the residual of the true input parameters versus the residuals we get, and then it's the 2 different distribution of signal to noise, a low signal to noise and a high signal to noise, and we see that for here we have 6 parameters, but really we're interested in the first 3 ones on the left. It's behaving really well for at least simulated data with noise. Now we switch to Apogee data, the data release 13, so Apogee data is about 200,000 spectra, I think, well, in this case, it's a little less than the 14 is more. So here we train with 15,000 stars, and then but we train importantly in individual visits. So a star might have several visits, and then by training an individual visit, you can actually get into a lower signal to noise, and you can sort of learn the algorithm a little better. And we get really good results as well by comparing to so the label here are taken from the AppScap official pipeline from the Apogee data, and same thing, we get pretty good results with this at various signal to noise. There's a little bit of problems at lower metallicity, but this is expected because the model doesn't really describe really well, and then we have very few stars in a training set. So now we could do is mixing both, where we actually train on synthetic and evaluate on the real data. So this is the same real data, the same synthetic data that I described, the same architecture, and obviously it's not going to be perfect because the description of the data is never perfect. And this is what we get here, larger scatter, same thing as signal to noise, the metallicity part is a little noisier. So it's got a few astrophysicists excited, so decided maybe we should keep going with this thing. It produced, so now we can apply it to the full data release, and it produced very human interpretable parameters, where here, this is just a traditional plot of the temperature versus surface gravity with a color scheme of metallicity, and then if you plot the isochrone, it sort of follows what you expect the physics will provide. As you can see here, this is the same plot, but with the training set represented on top. We don't cover so much on the training set on this particular region, and still we're able to do pretty well. So one thing we can do for fun, we can take the derivative of the big model of our parameters versus the spectra and make an average of things and see where, here's this temperature, surface gravity, and metallicity, and then where are the important part of the spectrum that we want to, that gives really power of prediction of those 3 parameters. And this is for the synthetic model, trained on a synthetic model, but when you train on the real data, then you can see you have several different things that no matter what, we'll have to work on that, but right now, it's fairly comparable. The sensitivities we can get are fairly comparable to a bunch of benchmark stock we took and compare with the optical data on the literature. Where we fail is when we have small data set to train on, and here this is a comparison of the Canon 10, the DR10, the first Canon, which was only trained with 540 stars, and we try to do the same, and then obviously then, as you can see, the residuals are not well behaved here. When we compare with the second release, the Canon 2, then we realize that we do much better, and then we do almost similar or better, or at least similar to the official pipeline. Missing data, now we're playing with other things. We're removing a few bunch of spots of the spectrum, see what are the influence of the stellar parameters. And apparently, even if we remove 3/7 of the spectrum randomly at training and evaluation time, you still get a fairly decent estimation of the parameters. Last thing that we're working on now, it's trying to mix surveys. So we're trying to get all data from SDSS, which was on the optical, and mixing with the Apogee data, put everything in this deep neural network and see what we get. And those are the residual of those two. This is just really work in progress. So we'll see what happens now. So this will be my conclusion. We have a really fast deep learning machine now that we can apply for several data sets. And then next, we're going to try to play with the generative models. We could maybe give us a little better estimation of the probability distributions. And maybe semi-supervised learning models to train only on synthetic, and both in synthetic and the data to sort of correct the synthetic models. Thank you.
Yeah, thanks a lot for the nice presentation. So, did I get it correct? In principle, the labels for your supervised learning, aren't they based on an algorithm, extracting that from the spectra? How do you deal with the biases of actually getting the astrophysical parameters through a software from a measurement and using that for training? Is this going in the direction of statistical post-processing, or could you perhaps say a word on that?
You mean, I'm not really sure I understand.
For your supervised learning, the labels you actually use, temperature, abundances,
yes,
those things.
We get them from the official pipeline.
Exactly, and so my question is, doesn't the learning actually just learn to do what the pipeline does?
Yes, but it behaves better as a lower signal to noise.
Yeah, so because I think it's doing some statistical post-processing.
Right, so it does also do things where the official pipeline doesn't do well, which I haven't talked about here, which is dealing with persistence. For example, there's this thing with persistence in the spectra, and we sort of autocorrect for this. There's other instrumental signature that we hope to also correct. This is work in progress as well.
Any other questions?
I have a couple of short questions. The first question is that there is also such a parameter as stellar rotation, which will mess up the things pretty strongly. And how do you plan to deal with this? Because effectively this is like a confusion, like a convolution function applied on the input of your neural network. And my second question is, how do you deal with the fact that actually people doing this atmospheric parameter determination, they cannot agree among themselves. The community cannot agree on which models to use and which approaches to use, because if you take those 150 benchmark stars, I'm pretty sure we're talking about the same sample. There was this paper where people compared like 10 different techniques and got the metallicity difference of 0.2 dex between the techniques, and every team claimed that our answer is right and all the others give the wrong thing. So this depends, like what training data set you use will actually affect the result of your classification.
So for the rotation, I'm not saying that this particular architecture will actually work for if we include rotation as a parameter there. We might have to, when we include rotation, we might have to work out a completely different architecture. For concerning the diversities in synthetic models, yes, this is actually something we're working on right now to see. We take different grids, different line lists, see if somehow we could maybe actually combine those different synthetic models and make a distribution of the models, what they actually covered in a parameter space, and maybe learn from that. This is some ideas we're exploring right now, really.
Thanks, Sebastian, again. Our next speaker will be Guillermo Guerrero, who will be speaking on deep learning in astronomy and its application to transient detection within the ALERCH system.
Funciona el puntero. Hay uno bueno. ¿Está bueno? ¿Está bueno? Hello, everyone. Thanks for having me up here again. So I'm Guillermo Cabrera. I'm going to talk to you about deep learning again. Lots of talk about deep learning. So you can see that this is kind of trendy. This is a collaboration we have built, which is called the ALERCE system. I'm going to talk to you about that too. But first, I'm going to start by talking about deep learning. So deep learning is basically model the data through different labels of abstraction. That's the concept behind it. And if you think about something like processing faces, if you see your colleague next to you and you want to classify him as your colleague or a student or whatever, what you first do is you, in your brain, have an edge detector with which you would start creating eyes and noses and mouth, something like that. And using all that information, then you create a face, okay? So deep learning is based on the neural system. So this is a neuron, and what we did was creating an artificial neuron, a mathematical representation of a neuron, in which we have an input, and this input is weighted, added or summed, and then gone through a step function. And if we have a neuron, then we can create a network of neurons or a neural network. So I guess most of us know about this. To me, deep learning, in general, it's like playing with a Lego for data scientists. So you have a Lego, which would be like your neuron, and with that Lego, you can use a small number of Legos and build something amazing, or you can use a huge number of Legos and again build something amazing. Okay? But I'm not saying one is better than the other one, right? It's just both are amazing, right? So the same thing happens with the neuron. You can build a very simple architecture, or you can build something much more complex. Okay? So what kind of architectures we can build? One of those is what everyone has been talking about, but mostly Josh, I guess. It's convolutional neural networks. And basically what you do is you create this set of neurons, which you place in a square, let's say, okay, or in a cube. And through those neurons, you create a small network that outputs a vector. Okay, so this is the same thing we showed before, but now I place them in a square, right? And that way I can, is this shown? Yeah, I can move that around the image, and according to that, I would create different vectors, right? Each one for each place I put this window in. Okay, and doing that, I can have my huge Lego architecture in which I can connect as many as I want to. I can use different images, different sizes, so I get to play with it. Okay? Another way that you can use neural networks is through recurrent neural networks. So what you do is basically you have your input and your output, but you connect your neurons with each other again. So what you're doing is you have an input, you have a set of neurons here, and the output of those neurons are connected as input to themselves. Okay, so if you expand this would look something like that. Okay, so as you're getting data in terms of time, right? So it gets x0, x1, x2, and so on and so forth. You can you'll have like a much more complicated neural network by using a very simple architecture, which is this one. Okay. And this has been very important, particularly by using long short-term memory and recurrent neural networks. And another really cool thing that you can do with them is what we call generative adversarial networks. And basically what you do is you have two models. You have a generator and you have a discriminator. And the goal here is that you make them compete. So you're generating new data. So let's say I want to generate faces. So I have this model that's generating faces, and I have real faces here. So I put my model to generate data, and then the discriminator is trying to realize if this is real data or it's part of my model. Okay, so I make them compete. And the thing is that after a lot of iteration and a lot of data, you get something sort of similar to a face. I wouldn't say you get a face, okay? But that's the whole idea. So neural networks are great, but you have to be cautious about them, okay? So building an architecture is not trivial, okay? You have to define the architecture. Deep learning models usually need to fit a huge amount of parameters, so that means we need lots of training time, and at the same time we need lots of data, okay? So one of the solutions is augment your data set, so you just create new data out of the previously generated data. But you always have to consider, you have to know what you're doing. You cannot use them as a black box. You have to know what you're doing there. And basically, for example, you cannot augment your data set and use that augmented data set as a training set, as a test set, as a separate test set, because you're already using it for training. Okay? So that's basically the idea of neural networks, but you have to use them wisely. Some tools, when I started working on this, like maybe 5 years ago, we started with Theano. okay? A student came up with, so Thiena was really hard to work with, okay? So a student came up with Caffe and said, we got Caffe. And then Google released their TensorFlow. And that was amazing because it was much easier to work with. And now we have even Keras, which is very, very easy to use. I mean, you can program a convolutional neural network in, let's say, 20 lines or something. So it's really, really easy to use. Some astronomy applications, well, as Josh said, this whole thing started with the Galaxy Zoo challenge, and the winner used rotation invariant convolutional neural networks. So galaxy morphologies have been one of these, the problems mostly where a lot of deep learning has been used. We applied the same architecture for high redshift galaxies, and it was amazing. We were impressed. Actually, we competed with these guys without using deep learning, and they kicked our, I'm not sure if I can say that, but we did very bad. And there's also galaxy morphologies for radio, transient detection and classification. I'm going to talk a little bit more in detail about this later. Basically, we built, whoops. There we go. So basically, we built a model that's able to detect transients on different images, and it was a huge it had a huge performance on our problems. There have been people trying to do this on multiband, and people from Galaxy Zoo combining deep neural networks with human classifiers. And also, you have recurrent neural networks for supernova classification. So in this plot, you see the flux of the supernova, and here you have the probability of being a type 1, okay? I think Josh mentioned this too, gravitational waves. There have been used in gravitational waves. They have been used for deconvolution. The generative adversarial models have been used for deconvolution. And basically, this is what they produce. I'm not sure if you can see this, but this is they have an original image here. They degrade it, and they try to reconstruct it, and they compare this with the deconvolved version. But I'm not sure if you can see here, but the recovered one has some stars that were not on the original. So imagine you have a model that creates fake stars. Would you use them? I would say no, but I think that this is a really important line where we can follow and do more research. Finally, they have been using this for image differencing, and you can grab two images and find the difference images using an encoder-decoder approach. So now I'm going to talk briefly about Alerce. This is basically it's a collaboration called Automatic Learning for the Rapid Classification of Events. And basically in 2013 and 2015, we had the High Cadence Transient Survey. We used data from DCAM, and we were trying to, we achieved to find supernova in real time. And we had to create the whole pipeline for that. And now we're having CTF, which will be generating 10 times more alerts. And then we'll have LSST, which will be generating 10 times more alerts than CDF, okay? So we're building this system. Oh, by the way, if you want to see more about this, there's a poster 105. Go and see it. So we're building this system that tries to get the alerts and rank them in order to know which one is more important to follow up, okay? What we've done is what I already mentioned, transient detection, and the idea is that you get we've done a lot of things, but this is one of them. And the idea is to try to classify the difference images in terms of if they are real or bogus supernovae. And this is our architecture. This is our complete Lego piece. And what we did was we used rotation invariant convolutional neural networks. The code is in Theano, but it's really easy to use. So we sort of build our own interfaces, and you can get it there. If you want to train your models, we'll be happy to train them for you. Okay? And the most important thing about this is that we achieved 5 times less real transients missed by using our convolutional neural network. So in practice, it was very, very useful. Okay? And you can see that our major improvement was done on the low signal to noise ratio supernova. So our model was able to get down below the noise. Okay, so we also have a demo for this. This is the GitHub. It's an IPython notebook, sorry, a Jupyter notebook. It's a Jupyter notebook that you can get access to it, and you can run our model, or a basic version of our model. If you need more help with that, I'd be happy to help you. And in summary, deep learning is a very powerful tool for astronomical data analysis. It may address different problems, but you have to be careful on how to use them, okay? You cannot just randomly get conclusions out of them, okay? It's not, as someone said, you input data and you get a paper out, okay? You have to understand what you're doing with them. Also, ALERCE, which is the automatic classification and reaction of events in real time, and we're using deep learning models among many other kind of models, and we're using them for everything. Light curve classification, image processing, for everything. But we're also comparing them against other models. There are people using information theory and stuff like that to create other kind of models. And deep hits, also I already show it. It's flexible and adaptable to any data set, and we're happy to train new models and help the community training their own models. So that's it. Before I leave, here are the GitHub. Whoops, what did I do? Here you go. Here are the GitHubs for this. We have a lot of posters, I mean like 6 posters from the collaboration, so please go and check them out. And the other important thing is that we're hiring, okay? So we need people, engineers, that can help us build the system. This is a huge system, it's a very ambitious project. So if you think you would like to come with us and work with us, we'll be happy to have you. Thank you.
Questions?
Thank you for the very nice talk. I have a concern that I hope others here have too, and don't make me a pariah, but so what I'm seeing with neural networks, everybody uses them, it's a great machine, and like as a car, for instance, I don't need to understand how a car works to use it. But I don't see much mathematical understanding of what's actually going on, and what do you think, or could you comment on what should happen or what must happen in the next year so that they become more useful than just, black boxes that work?
So that's a very, very good question. And there's a lot of community. So the problem with neural networks in general is that they work perfectly. We all know they work great in really challenging projects or problems, but the problem is no one knows why they work, okay? So there's a lot of research around that. People trying to understand why they work, and actually we're working with that with some students, and we're addressing that problem through an information theory perspective. So we're measuring the information loss between while you're going deep into the network and out of it. So it's a very important question. So I would say there's no clear answer right now why they work, but we all know that they work, and so it's So if someone comes up with the answer for that, that would be very important.
There's a question up in front.
There.
And there's one back here.
Actually, to quickly answer the question why they work, you should go back into the history when they all started. Neural networks, it's nothing else than a set of nonlinear, than a nonlinear filter that gets some input and creates an output, the one that you trained it to do. In fact, training, it's assigning the weights to those things. So there is some understanding why it works, and there is also understanding why it doesn't work when your training data set is incomplete. If you try to take, for instance, those images from, one of the packages from Google and train it on images of cats and then ask it to classify an image of a dog, obviously it will tell you that it's a cat because it has never seen a dog before. And exactly the same way people use networks, for instance, neural networks to do photometric redshifts. Probably many of you are aware of this stuff. And one of the cases that I encountered personally is that a few years ago, we had a very promising galaxy candidate at Redshift, I don't know, 8 or whatever, and we spent 24 hours with Magellan trying to observe it, 24 hours of integration time, and we got a beautiful spectrum, we saw the continuum, and then we realized that it was a T-dwarf. And then it turned out that T-dwarfs were not in the template library for the classification. They had L-dwarfs, but they didn't have T-dwarfs. And so this was one of the objects that neural network didn't know about. Since then, they included them. But you know, for us, bad luck.
Mm-hmm. So actually, that's a problem. I mean, there are lots of biases in every machine learning model. And in that case, you had a problem with the selection of your data set. I mean, you were trying to predict for something that was not in your training set, right? And yeah, that's a very important question. Actually, we're going to talk about that in the Birds of a Feather session in the afternoon, so we would be happy to have you there.
I'm wondering if your detection pipeline would be capable of detecting moving objects.
So that's a very good question. And actually what we did was we trained on a G filter where we wouldn't see the moving objects, okay? And, but when we applied it to U filter, we would detect the moving objects. So the moving objects, so the problem is that they look like a transient, but they're not a transient, right? And in that sense, we needed to somehow take that into consideration when building the training set, okay? So we worked around that. That was a problem. So that's why we had to train on a filter and then apply it to a different filter. And in order to evaluate on the new images, what we did was, in the end, after the run, right, we already have detected and confirmed some supernova, and over the supernova that we have already confirmed, our model worked much better than the random forest model.
Okay, let's thank our speaker again. Our next speaker is Alessandra Solars, speaking on automated novelty, detection in the WISE survey with one-class support vector machines.
Thank you. These two. Okay, hello? Okay, thank you. Hello, everybody. My name is Alexandra Solars, and I'm currently working in the National Center for the Nuclear Research in Poland, and I'd like to talk about the automated novelty detection in the WISE survey. So usually the SKY surveys are designed to provide as large and as deep as possible statistical samples of astronomical objects, aiming at the best spatial overview, completeness, and homogeneousness of those data sets. So then later we can draw some general conclusions about the abundant objects that appear in this survey. Another attractive role that they present is that we can search for some rare and unusual objects that could just so happen to be caught by the survey. So one of the widest and the deepest publicly available SKY surveys right now is the All-Sky survey performed by the Wide Field Infrared Survey Explorer, WISE. It has scanned the whole sky in 4 infrared pulse bands covering the wavelength range from 3 to 22 micrometers, and it has detected over 750 million sources, which amounts to around 15 petabytes of data. The drawbacks of the survey are that WISE has quite low angular resolution, which is around 6 arcseconds. So this means that in the area of high density, we are risking blends. And the second one is that on board of WISE, there was no spectrograph, so we have no redshift information about the sources. That means that we don't really know what type of objects we are looking at. However, that is the reason why WISE is the perfect playground for digging for some rare and unusual sources. So the usual approach to the source selection and the selection of some novelties is the exploration of the parameter space, like, for example, the classical color-color diagram. Here, different types of objects will appear on different parts of this diagram due to the different physical processes that govern them. And the new or novel sources are usually selected by their deviation from the expectation zones. However, more often than not, such new or unusual objects they are hiding in the bulk of the normal objects, mimicking their behavior. So the human selection is imperfect and a lot of information is lost. However, the computers are way more precise than that, and they can not only deal with a lot of more data at once, but they're not restricted to just working in 3 dimensions like humans are. So machine learning is very necessary when we want to select new objects. So before we can select new objects, we actually have to know what we are expecting. So we have to find the training set. Since WISE has no redshift information, I had to find the training set somewhere else. And I did that by a cross-match, a positional cross-match with the Sloan Digital Sky Survey, a survey which is wide enough to cover big parts of the WISE survey, and it actually provides the spectroscopic information about the sources. So by this cross-match, I could find 3 general classes of stars, galaxies, and quasars. And then, of course, we have to select the parameter space in which these unusual sources will hopefully stand out. And to do that, I selected the near-infrared fluxes, colors. I didn't use any mid-infrared observations, simply because the signal-to-noise ratio is quite high, and therefore the detection rate drops. So in order to preserve the amount of objects, as large amount of objects as possible, I didn't use them. Additionally, I have created a parameter which measures the compactness of the source, which is simply the difference in the observed flux in one filter, just measured through 2 different apertures, sizes of apertures. And it is also a nice way to clean the data from all the possible blends that the WISE survey can have. One of the algorithms that allows for the detection of some outlying sources is the one-class variation of the classical support vector machine algorithm. Here, instead of using the multiple classes of sources, we can create one known or expected class, and in this case it was a mixture of the galaxies, stars, and quasars detected both in WISE and SDSS. And then, as SVM does, it maps the input data from the input parameter space to a higher dimensional feature space, where it creates a kind of enclosed hyper shape, which will hug all the known classes. And then, when we apply the new data, the remaining data, everything that the machine did not learn to recognize should fall outside of this sphere, and it will be marked as a novelty. So we have applied this algorithm to the WISE data, and we found around 650 sources with unexpected patterns. So since they are potentially presenting some new and exciting objects, we of course investigated further what they are. And the first group of the sources is unfortunately spurious. They have very blue near-infrared colors, and when you take a look at their distribution all over the sky, it turns out that they are almost exclusively confined to the galactic plane and galactic bulge. To confirm that they are spurious, that they are blends, since WISE has a low resolution, We cross-matched these sources with another infrared survey performed by Spitzer. It is also performed in the infrared, but it has a much higher angular resolution. And indeed, you can see where WISE has seen one nice singular source. In actuality, these are two very close-by sources. So if anything else, the anomaly detection algorithm presents a nice way to clean our data from all the unexpected artifacts. And the second group of the anomalies that we found is much more exciting. This group has very large, very red near-infrared colors, and their discriminating property is that the observed flux grows drastically with the observed wavelength. So it is quite clear that these sources cannot be stars, because no starlight can be redshifted to such long wavelengths. So this emission must come either from warm dust or from the polycyclic aromatic hydrocarbon emission lines, which are characteristic for the star-forming galaxies. So in order to confirm that assumption, we were trying to find any counterparts in any other publicly available sky survey. And as we found, almost 90% of these sources are undetected at other wavelengths. What we could find is around 2,700 objects with an optical counterpart in the photometric part of the SDSS survey. So this means that they do not have the spectroscopic redshift information. The only thing that they provide is the flux measurement through the 5 SDSS filters. However, this already gave us some insight about the nature of these sources. When we combined the optical and infrared fluxes, it turned out that the distribution of these sources is bimodal, so we are possibly looking at least 2 different populations of sources. And since we do already have quite a few points, photometric points, we could perform the photometric redshift estimation. And thanks to those photoz's, we could perform the spectral energy distribution fitting in order to find out some rough estimates about the properties of these sources. And what we found is quite exciting because all these sources appear to be extremely bright in the infrared, and their luminosities of dust exceed 10 to 11th solar luminosity. And what is even more exciting is that almost 50% of this emission comes from the active galactic nuclei source. So even though these objects are not a new type of object, they are quite rare. There are not many samples of such objects. So for the remaining sources, anomalous sources, we do not have any additional information. So their nature remains unconfirmed, and hopefully we will get some time on the telescopes to get some spectroscopic information about them. So to conclude, we are now living in an era where finding some unusual objects which present some new physics, hopefully new physics, we can find them with the machine learning anomaly detection schemes, and we should search for those, we should account for those unknown unknowns in the data. And anomaly detection algorithms present not only a nice way to clean the data from the spurious sources, but also to find those previously unclassified sources. Okay, thank you.
Questions?
But they are quite bright in the radio, yes. So hopefully they are really AGNs.
Any other questions?
Okay, let's eat.
Let's thank our speaker once again. I have just a quick announcement about the focus demos before we go to lunch. There will be 2 focus demos starting at 1:30. One will be by Ishmael Pesseh, and Python Muse software for data analysis. The other will be by Roberto Gonzalez on AstroCV, a computer vision library for astronomy. We'll see you after lunch.